Hello everyone. Vitis HLS makes it easier to design efficient kernel with AXI master interfaces. As a starting point, let's look at this simple example to see how we can optimize bandwidth. First, let's apply the interface pragmas. They are not required since pointers automatically map to AXI master in the Vitis flow, but it's good design practice to apply them. After running C synthesis, we will notice that all the pointers are attached to the same HLS adapter, which creates a bottleneck as there aren't enough wires to read our two inputs simultaneously while also generating the output result. The adapter that HLS uses has two parallel independent paths, one for read and one for write. So when optimizing a design for bandwidth, we want to make sure that each adapter has only one read and one write path at the most. Of course, this is a trade-off, since using more adapters makes the kernel a little larger, but here I'm going to assume that we are looking for best bandwidth. Sure enough, the platform for which this kernel is designed and the Vitis V++ compiler option will also play a role in establishing an optimal bandwidth. But here, we are only focusing on the kernel design. So I now created a new adapter via the bundle keyword on the input called in1, and this now results in two AXI adapters, one just with in1 and the other with in2 and out. None of them are saturated. I can also confirm based on the C synthesis results that the initiation interval, the II, is 1, and that the loop is pipeline, which is a default behavior in Vitis HLS. Still, the interface remains at 32-bit wide because we are processing integer data types. But we were hoping to have the tool widen the interface to 512 bits to take advantage of the IP capabilities of the platform for Alveo accelerator card. Once we check the solution settings in the HLS tool, we do see that the MAXI interface option to widen the bit width option is already set to 512 bits, but we didn't get 512, we only got 32 bits. Well, the reason is that the compiler wants a guarantee that the data transfers align to 512 bits. So we're going to need to modify the source code to make it clear to the compiler. In this modified version of the code, we implemented a second change in the for loop condition expression. We're using the integer scalar input size divided by 16 and then multiplied by 16. This ensures that our loop aligns to a 16 times 32-bit, which matches a 512-bit boundary. Then our next step is to unroll the loop by a factor of 16, such that every integer on the wider bus is processed at each clock cycle. This in effect creates 16 parallel processing lanes that I would loosely call threads. After C synthesis, we can verify the parallelism in the schedule viewer of Vitis HLS. So here's the result after making these changes with the adapter code change, then to the termination loop variable, and then adding the unroll pragma. We do have a wider interface that we can verify in the waveform viewer of Vivado. As you can see, the waveforms are organized per bundle, gmem and gmem0. We can see the in2, the out, I can also see the in1, and I can verify that there is concurrency between the read and the write operations to the output. In this simulation, I am sending 1024 integers for both inputs, and I do see the expected 64 clock cycles with 512-bit wide buses in the RTL co-simulation launched from the Vitis HLS IDE. Alternatively, note that we could also use the new vector data types introduced in Vitis HLS 2020.2 to explicitly control the widening of the ports on kernels. This variant would also be applicable to the Vitis HLS IP Vivado flow. On this slide, you can see side by side the differences in coding style between using vector data types versus relying on the widen option of Vitis HLS. The vector data type gives you a simpler coding style with explicit widening, but you have to rely on that special data type. Without vector data types, one advantage is that the function signature is same, which is a good thing for the Vitis flow since it implies that you don't have to change the host code. Still, you may need to use the unroll pragma, and you will rely on the bit width widening option. In summary, the new version of Vitis HLS automatically widens the AXI master data width if accesses are aligned to the value set for the bit width parameter. Alternatively, vector data types, which are also supported in Vitis HLS, help specify port width in a more direct manner. Thanks for following this video, goodbye and have a great rest of your day.